All right, thanks everyone for coming back from the coffee break. We've got a technical session now. We're happy to have Shiva Kasiviswanathan, who's been doing great work in differential privacy for a long time now, decades. At least one decade. We're going to hear about contextual online false discovery rate control.
Thanks, Aaron. So my name is Shiva Kasiviswanathan. I guess it's great to talk about this topic here because I think this is a topic that I first heard right in this room about 5 years back when I think we had a first workshop on privacy, and Benjamini gave a talk on false discovery, I think it's 2013. I didn't think about it for 5 years, but just recently we thought about it again, and I joined work with my intern, Nishian Chen. So the problem that we're going to discuss is false discovery, which has been in the news lately. I mean, it's a very important problem in the scientific community because it affects what we believe to be true or false. And so controlling false discoveries is a really important problem, especially when you want to get to valid statistical testings. The problem is very important because in modern scientific analysis we have lots of hypothesis tests that we are carrying out, because if you think of a typical microarray experiment that is common in DNA sequencing, is that we carry more than 10,000 tests for each microarray. And what happens when you do so many tests is the chance of spurious discoveries, false discoveries. So let's run through a simple example to see what is meant by false discovery. So let's say that we are running 10,000 independent statistical tests. Okay, let's, for simplicity, assume that 9,900 of them are actually negatives and 100 of them are positives. Okay, so this is the ground truth. So 9,900 of them are negatives, 100 of these tests are positives. Okay, so let's say that we set your alpha, the significance level of these tests, to be 0.05. Okay, so you take 9,900 times 0.05, that's 495. So you get about 495 false identifications. And let's say the power of these tests that you have is really great. It's 80, which is a really high number. So you get 80 of them true positives out of the 100 actual positives. So now if you look at the ratio of these things and the number of the false discovery divided by the number of total discoveries, that's 495 divided by 495 plus 80. That's a number that's really close to 1. Really bad. So notice that this is not a problem with the tests being dependent on each other. This happens even if the tests are independent, if the data is independent, and so on. So this is not a problem with the tests being dependent on each other. It's just a problem that we are running so many tests. So that's the problem when you run multiple tests. So that's the question is, how do you control for the spurious discoveries in the setup? Okay, so this is a problem that's been there for many decades, but it was kind of formalized in a very precise sense by Benjamin and Hochberg, who introduced this notion of false discovery rate control and introduced a notion that is used to control false discoveries when you do multiple hypothesis testing. This was in the offline setting. About 10 years ago, Foster and Stein introduced this notion of online false discovery rate control, which moved the setting from offline to an online setting. But this work is about adding another prefix to this, and we're going to talk about a slightly different model, which is called contextual online false discovery. So I'm going to explain all what these terms means in the next few slides. So starting with what the false discovery control is in an offline setting in a more precise sense. Okay, so let's go into the offline multiple hypothesis testing problem. So you have n hypotheses that you want to test, h1 to hn, and we assume that each of them has a p-value associated with it. Let's denote by p1 to pn. Okay, so think of a multiple hypothesis testing procedure, script R, as a test that takes these p-values and returns a subset of hypotheses that has to be rejected.
Can I just ask you something? For those of us who are non-technical in the audience, could you, from time to time, say, for example, and then give us a concrete?
Sure.
Like, what is the hypothesis?
What's the hypothesis? Okay. So I mean, the hypothesis. It could be anything like testing for think of a test that you do for whether a gene is associated with a trait. Okay, whether a gene is associated with a trait. For example, a mutation in the gene could be associated with an increase in height. And now you get data for this, and then you test whether this hypothesis is true or false. So you basically form a null hypothesis, which might be saying that it is not associated, and you have an alternate, and then you see which one should be. So either you reject or accept the null hypothesis. So that's typically a test. And so and you might do multiple of such tests.
So maybe, would it be helpful just to hear sort of the problem set up so far in plain English in a sentence or two? Is that, yes? Okay.
Yeah, so I guess.
Or I can try.
Yeah, I mean, I guess, so is that clear? I mean, like, so a test is some kind of a statistical.
So then now just.
Yeah, so now the issue is if you test a lot of hypotheses, so you check for every gene in your body whether or not it's correlated with a particular outcome. Even if your tests are reasonably accurate, just because you checked so many different things, a bunch of them are going to spuriously look accurate. And sometimes the number of things that look like they're correlated, it is pretty, is some large number of things, but actually most of those things that looked accurate according to the test are not. And so then, your test looks pretty useless. And so there's this concern, as you do multiple tests, how do you interpret the findings?
Okay.
Yeah, I mean, I guess the idea is that we want to get to a procedure where we're not making false positive discoveries. We're not making discoveries that are just spurious by chance. So we want to create a procedure when you do multiple testing, can control this false positive. So that's the hypothesis. So basically, hypothesis testing procedure, or multiple hypothesis testing procedure, takes a bunch of these hypotheses and returns a set of hypotheses that has to be rejected.
I have a question.
Yes.
So if it's truly ideal, if you had enough data and you knew the hypothesis distributions, shouldn't it converge to your guarantees on?
I mean, what do you mean by? I mean, the tests are independent, right? So the tests are independent, right? So even if you do the independent test, the fact that you have set your alpha to be 0.05, I mean, as in the previous example, I mean, you could have spurious discoveries. That's just because by chance, right?
For a fixed data set size.
Maybe the disconnect is like a frequentist versus Bayesian perspective. Like the p-value is telling you like a frequentist quantity, and if the true probability of the null hypothesis is very high, then it might be that, even if all of them are true, you come up with a large number that appear to be false. Some of this would be avoided if you really understood the prior, but
yeah. So that
Or estimated it really well from the data.
Yeah, I mean that would be changing the p-values in a different sense. Yeah.
So just to make sure, I'm not going to test the same hypothesis multiple times ever in this. Like I'm going to test all different genes for correlation with height.
Yeah, yeah. I mean, there's no point in doing that, but yeah, but you're testing multiple. Okay, so what happens? So let's understand this slightly better. So let's say what are the all possible outcomes that when you do multiple hypothesis tests. So in the rows there are what happens, what's the true, and this is what your test is giving you. Okay, so there are 4 possible outcomes in this confusion matrix. I mean, you could have a hypothesis that's truly null and you accept it. That's a good case. Okay, or you have that's a truly alternate and you reject it. That's also a good case. But you have also have mistakes in the other time. So the notion of false discovery rate, which was introduced by this work by Benjamin and Hochberg, formalized this and said what this should we control? What's the notion that we should be looking for control? So let's start with the notion of false discovery proportions, which is defined as the number of discoveries or number of false discoveries. So that's V divided by the number of rejections. That's R. The symbol R or 1 is just max. Okay. So the false discovery proportion is the number of is a proportion of false discoveries that you're making. So there is number of false discovery by number of total discoveries. And this is a random variable subject to the randomness in your test and so on. And so you're looking at the expected value of this, which is called FDR. And that's the notion that we're trying to control. So FDR could be thought of an expected proportion of the type 1 error in a test procedure. If this is basically like looking at the type 1 error and you're controlling that, that's your FTR. Okay, and so in the offline setting, a Benjamini-Hochberg procedure is a very popular way of controlling this FTR. That's been studied for the last 35 years now.
So I have another question.
Yes.
But why isn't this a problem just saying how good is the p-test compared to the Newman-Pearson test if I knew the true distribution?
So this is, again, this is not looking at the, like.
So you're married to the p-test in this case, and so then you have to fix.
This is a problem with multiple tests. It's not looking at the optimality of tests or anything. This is, you're not assuming anything about the test per se. You're just saying that you have multiple of these tests and you want to prevent the number of spurious discoveries. So it's not really married to the optimality of these tests.
Like the Newman-Pearson test, I think, would be like an example of a test statistic that you could compute a p-value for.
Yeah. So the other side of this problem is also this notion of statistical power. So because you really don't want, it's easy to control for FTR. Like similarly, as it's easy to control privacy, so you also want to talk about utility. So the notion of utility in this concept would be the power, statistical power of these tests. So while we want to control FTR, we also want to increase the power. So the power is the number of the true discoveries that you're making, the number of null hypotheses that are truly rejected, the number of alternate hypotheses that are truly accepted. Okay, so that's the true discovery proportion. That's defined as the S, which is alternate is true and you reject it, divided by n1, which is basically the number of alternates that are true. And again, this is a random variable, and the expected value of this is known as the true discovery rate. So the idea of this entire line of work is to basically ensure that you control the false discovery while maximizing the true discoveries. So these are the two things that you want to control. You want to control FTR and you want to maximize this. Okay, so that's what happens in the offline setting. And so what happened in the last 10 years is that we moved to a more online setting where the tests are coming in an online fashion. Okay, so what's happening is, like, if you are looking at offline setting, you assume that all the hypotheses and all the tests are available beforehand, and you're basically controlling the false discoveries, knowing all the results. So you assume that you know all the p-values, and then you design a test that controls the FTR while maximizing true discoveries. Okay. But that doesn't happen in the real setup. So in real setup, the tests are not fixed a priori. You have tests that are carried one after the other. Let's take a simple example. So let's say a company that's doing an A/B testing on a web page. Okay, so you're looking at whether you're looking at the click-through rate on a web page. So now you might set up an hypothesis saying that changing the color would increase my click-through rate, will make it more likely that people will click the page. Okay, so based on that result, you might create another test saying that depending on how the color looks, if I put it on look at a mobile version, how does my click-through rate changes? So, and you might construct a sequence of these tests based on the results of the previous test that you already have. Okay, so the hypotheses are not known a priori, they come over time in a stream. Okay, and so now each time you have a new hypothesis and you want to decide whether to accept or reject the hypothesis. Okay, so this is what the online multiple testing problem is. So you have a sequence of ordered hypotheses, H1, H2, and so on, and each arriving in a stream with a possible p-value, p1, p2, and so on. And at each step, you have to decide whether to reject the current hypothesis without having access to hypothesis that's coming in the future. So you just have access to what's happened in the past, and you have to decide at that moment whether to accept or reject it. Okay. Again, the goal is to control the false discovery rate and maximize the true discovery rate. Okay, so what's changing now is that you have this alpha, the significance level that you're designing for your test. Yes?
I just have a question. In the online case, do we still assume all these hypotheses are going to be independent?
We would get to that in a moment. Yeah. So you make various assumptions, and that will affect the power and FTR control. Okay, so online testing procedure takes a sequence significance level. So instead of creating one alpha, what you're going to do is you're choosing alpha based on what you have, what you know at this time t. So you have this alpha t at every point t, and then you're going to basically reject or accept based on that p-value. And so you compare pt, that's your p-value at current time t, with respect to alpha t, and if pt is less than alpha t, you reject, otherwise you accept. So now the goal is to come up with these significance levels that are a function of all the previous decisions that you have made at every time step t. So one can just go ahead and define FTR again in this online setup. I mean, it's almost the same, just that you have this time subscript added out. So the false discrete proportion is basically number of false rejections divided by number of rejections, and the expected value of that is FTR at time t, and you want the supremum of this over all time steps to be controlled by alpha. So that's the goal in an online setup. Okay, so the challenge here is that you don't know what's happening in the future. You have to basically accept or reject based on what you have seen so far. Okay, and then we can similarly define true discovery rate in online setting. So as I said, this problem was introduced about 10 years back by the work of Foster and Stein, and there has been some really good work in the last few years of creating rules or procedures that do online false discovery rate control. A general class of these rules is known as generalized alpha investing. I'll get to this in the next few slides. And there was some specific instantiations of this generalized alpha investing. There's a technique called as LOD, levels based on recent discovery, and there's some technique called as LOD++, which just recently came. So these are all specific sub-examples of this notion of generalized alpha investing that we'll get to in a minute. There's also a slightly different technique called saffron. Again, this is slightly tangential to this line of work, so I'm not going to discuss that, but if you have questions, I can talk about this, because this is based on something called as Story's procedure, which is a different variant of Benjamin-Hodgkin procedure. But let's focus on GAI, generalized alpha investing. Okay, so what is contextual information? So I started with offline hypothesis testing. We went to the online model, and now I need to add this word contextual. So what is contextual information here? So what happens is that typically when you do these tests, in addition to the p-values, you also have some side information. I mean, you might have that you have related to the test. And this side information or contextual information is something that you can utilize to make your test better. Okay, so I mean, I guess roughly you can think of contextual information as some indirect information that measures the likelihood of a hypothesis that is tested being false, but you don't really know the relationship ahead of time. So it is some kind of indirect indicator of the hypothesis being false, but you just don't know that information, what the relationship is exactly a priori. Okay, so this could be any information. So let's maybe, I think Helen has this question, so let's make it more concrete. So let's take some examples and see what could be a side information in different setups. So we were talking about A/B testing of a web page, and you're looking for the changes in colors and the effect on click-through rate. But the side information could be the size of your banner ad or the content on the text on the page, right? I mean, these are all side information which are not directly relevant to the question that you're asking about whether color is influencing the click-through rate, but it could be information that could play a role in your analysis. We discussed about a gene with a trait. So there's a really important questions about whether a mutation in a gene is causing a trait. Okay, so I mean, that's the question that you're looking at, and you're looking at the correlations of these gene with the trait. But it could matter that the location of the gene would play a role, or the count of the genes or chromosomes could play a role. In general, there are notions of machine learning, and there's problems of disease prediction, and you're looking at whether a person is predisposed to a particular disease, and then the biological information of a person could play a role, graphical information. Yes?
Elementary question. When do you decide that something is contextual information, and when it's why do you decide to put it there and not wrap it into the hypothesis?
Yeah, I mean, so it's a great question. For example, I mean, this is something that the test person, I mean, the investigator would be doing this. I mean, so what's happened, for example, in the gene studies? I mean, the general problems are looking at correlations. I mean, they would just look at correlations with the mutation, a mutation of a gene with a height, for example. That's very thing. And that's the test that you're doing. I mean, you could design a different test, but like you can use already the contextual information to influence the test.
Maybe like
Yeah, so in this work, we are not going to be discussing how do you decide the contextual information, but the fact that contextual information is given through some way. I mean, that's a
yeah, maybe like concretely, like the way, like to compute a p-value, you have to know the distribution of your test statistic if your null hypothesis is true. And so there's a lot of reason to formulate a simple null hypothesis so that you can like calculate that. So even though you might prefer to have all of the contextual information, that would make the like statistical analysis too hard.
And so yeah, so I guess there's a long line of work in the offline setting in utilizing contextual information. I think, and this is I think some amazing connections to also the with adaptive data analysis and so on. Okay, so what's contextual online multiple hypothesis testing? So it's a problem where you have a sequence of hypotheses that are arriving in a stream again. So instead of now, in addition to the p-value, you also have this contextual vector coming from some contextual space. That is the additional information that you have. So again, the goal is the same. At each point I, you have you have to decide whether to accept or reject the hypothesis, null hypothesis. And again, you want to control the FDR and maximize the number of true discoveries. Okay. So the main thing is that one thing you should remember is that the hope is that one can use the contextual information to improve the number of useful discoveries, right? And because you can always ignore the contextual information and just use the p-values and use the previous procedures to control FDR. So the main thing to think about is that hopefully the contextual information is going to help you improve the number of true discoveries. Okay. So what changes is that now your alpha t, the significance level at each time step, is now a function of not only your previous rejections, but also the function of a contextual information. So you have this x vector that's coming up every time, and your alpha t is defined as a function of all these things. But the things remain the same. So you will define your alpha t, and then you check with your pt, and if pt is less than alpha t, you reject, otherwise you accept. Okay, so that's the introduction to this talk. So let's in the last 5-10 minutes, I will explain what the results that we achieve in this setting. Okay, so any questions about the setting? So we started with offline, online, and then contextual online. Okay. So the main thing that we want to focus is that we first want to show that there's FDR control. I mean, it's like the essential step. And as I said, the FDR control is only one side of the coin. You want to also look at the power of these tests and hopefully show that the contextual information could lead to increase in power. And I don't think I have time for experimental results, but we have experiments. Okay, so let's talk about. So I said so the way we do FDR control is by kind of generalizing this, starting with this notion of generalized alpha investing rules, which have been introduced by Aroni and Rosset in the online testing situation. And we introduced a new class of testing rules or procedure called contextual generalized alpha investing rule. So I'm going to just briefly explain what these rules are, and then say what our extension would be. So if you look at this, there is a notion of alpha investing. So it has to do with something with investing and some money and so on. So I think that's the idea of this generalized alpha investing rules. So what does this do? So let's say that you start with some budget. So that's your alpha value that you have for your testing procedure. And the idea is that each of these tests is going to use some wealth of this. So you pay some penalty for doing a test. Okay, so after the test, you lose some money. Okay, and so each test will cost you some money. But each discovery, you get a reward. It's a very simple setup. So every time you do a test, you pay something, and every time you make a discovery, you earn something back. So that's generalized alpha investing in pictures. You can mathematically define this. So you start with some initial wealth, which is a number between 0 to alpha. Then at every point, you have a wealth update. So you pay a penalty function phi t, and then you get a reward if you make a rejection or a discovery. Okay. So the main thing is to ensure that nothing breaks here. So you can't have the wealth to be negative. So the phi t should be less than wt minus 1. Otherwise,
Do you just receive the wealth if you make a discovery?
Yes, every time you make a discovery, you get.
So you invest it every time t, and then you receive a reward only at certain.
Yes. Yeah. So the fee t goes every time, but every time you make a so RT is 1 or 0 based on whether you make a rejection, and if it's 1, you get the reward. Otherwise,
So you cannot change your mind about rejections or acceptance?
no. You make a decision at the time t. So once it's done, it's done.
That's the offline part. The online part, right?
Yeah.
Right.
Yeah, you don't know the future also. So so there is something vacuous here. So basically, one more thing that we need to do is to make sure that you can obviously need to control. You can't give an arbitrary amount of reward at every time, because then otherwise this problem is you can just make WT to be anything. There has to be some control on the wealth or the reward that you can give at every point in time, and that comes through a complicated equation. I mean, we won't have time to go through it, but in a way it comes to when you do when you analyze this the proof of this FDR control. So the goal would be to construct these functions phi, psi, and alpha. I mean, so they all lie in the sigma field of these R1 to RT minus 1. That's basically the previous decisions that you have made. So what happens in this with the contextual information is that you basically change the sigma field. So you're changing your instead of just the previous discoveries, you also have these contextual information that you have to account for. Okay, and I mean that's what we define as contextual generalized alpha investing rules.
What's the sigma notation?
The sigma field of these, so it's just an even
Just
space.
some function of those things.
Yes, it's just so that's something that we can realize.
Got it.
So one more thing that we need to add is this notion of monotonicity, which is a very conceptually a simple rule to say that if you are making more rejections, then your threshold should be significance level should be more. So that's like a simple additional constraint that we need to add. So in addition to the previous constraints, we also had this monotonicity, and then basically what we can show is that if the p-values are independent, and the crucial thing is that the p-values are and xt's are independent under the null, then any rule from this class would satisfy FDR control. So the point to note is that the p's and the x's could be arbitrarily related under the alternate. They are only required to be independent under the null. So under the alternate, obviously otherwise there's no really thing that you can control for. So they are only independent under the null. They could be arbitrarily related under the alternate. And this is, I think, I answered this question. So, but this is not the only thing you can show. You can show actually, you can relax you don't have to be p's to be independent. You can show weaker assumptions on the p-values, super uniformity, PRDs. You can have actually arbitrary dependence on p-values. You obviously have to be more conservative in that case.
Shiva, I don't want to slow you down, so feel free to say no, but is it okay to ask you to give us an example, to repeat the example of how the context can, how I would use the context to get higher power here?
Yeah, so I think that's a theorem that we're going to show later on. But that would be the goal. We would, can I get to on those slides and then I'll get back to you. But yeah, so the idea is that, so FDR control is something that's possible under the contextual information by changing these, by creating this any monotone contextual generalized alpha investing rule. Skip the proof idea. This is all important. So basically, get into the second part of this talk. So as I said, the FDR control is just one piece of the puzzle. I'm going to talk quickly about what you can do with that. I guess the point is to ensure that you have increase in statistical power. And the answer is yes, and it comes with a big asterisk because it's really hard to analyze statistical power in vacuum. This is true for any test, not just our test. One has to define a set of pieces, and you can only analyze power under those conditions. So we have to define a set of rules, then define the model, and the conditions under which these hold. So there will be three pieces that we have to define for this to happen. So quickly, what happens is that the way we define our set of rules is basically define a specific subclass of these contextual generalized alpha investing, where we are going to use the current context to define a weight function. So we are going to convert the x's into a weight, and we are going to weigh the significance level using this weight function. So we are going to look at a subclass of this general class of rules where this specific thing happens. And we are going to focus on something known as LOD. LOD is a popular subclass of these generalized alpha investing rules. And what we are going to do is we are going to define a mixture model, a pretty general mixture model, where the main thing to notice is that we're going to assume that the x's have different probability distribution under the null and an alternate. And we'll have some conditions on these mixture distributions.
So the idea here is that your context gives you a weak signal about whether or not the hypothesis.
It gives you a weak signal about the likelihood of the alternate. But you really don't know the signals. So you know nothing about this. You're assuming that x is drawn from these distributions L0, L1, and the p-values under the alternate is coming from some distribution F1. But you have no idea of these L0s, L1, or F1. Okay, so you really don't know anything about them. But the assumption is that under the null, they're coming from the uniform. Under the alternate, they are coming from some arbitrary F1.
And what role does the context play in here?
The context.
What part of this is the context?
The x's are the context. The p-values under the alternate is defined using this F1, right? So I mean, the main thing is that it captures standard models like normal means model, where you're testing for whether Gaussian has a mean 0 or non-zero. And the main thing what we show is that we define a notion of informativeness of when and show that if your context has some informativeness property, then you can have a separation between what you achieve without using the context and what you can achieve with the context. So you apply the same procedure LOD without the context, and you apply the same procedure LOD with the context. And if the context has some notion of informativeness, which is really an intuitive notion, which basically says that the weights are higher under the alternate, then we can show a separation saying that you would achieve more power than without context. Makes sense? So
if I understand correctly, you want to accept more readily when you think the alternate has higher likelihood. You want to reject. You want to declare a discovery. You're going to be give yourself sort of more space to declare a discovery when you kind of think a priori the discovery is true, and when you think a priori the discovery, like the null is the case, you sort of set a more stringent standard.
Yeah. But the context has to have some information, right? I mean, the context could be independent of all these things, and so you have to have context has to somehow relate to the alternates, right? Otherwise, you obviously can't get anything. So formalizes this notion of informativeness that we define. And when it satisfies the notion of informativeness, we would say that we have more discoveries. We would theoretically show that there is a separation in the power with and without using context.
We're running a bit over time, so
yes.
All future questions can be done over.
Yeah, so I think so one of the things is that this actually helps in practice. I mean, so that's the main thing. One nice thing about these problems is that once we define this in this way, as I said, you're using the weights as a weight x's as a weight function. You can define any parametric form of these x's. We in fact use something based on neural networks, and you can train these neural networks using x's to discover. So that the goal would be you would train these networks where you have a hard constraint on FDR, but you want to maximize the number of empirical discoveries. You can train these networks in that online fashion by imposing an FDR control constraint subject to maximizing the number of discoveries. And you can, it really works remarkably well compared to other procedures that we know of. Because you can suddenly get even like 20 to 30% improvement by just using this contextual information. Okay, so this is running out of time. So the idea is that we introduce this, concept of contextual online FTR control and propose a new class of rules that do that. There is theoretical analysis of FTR control and power improvement with better empirical performance. So one thing that we haven't done now, I think is really interesting, is that this notion of informativeness is really a condition on the distributions, and it's not clear how you can do that in practice. How do you check for these, whether you in practice whether your informativeness is satisfied? Okay, and the procedure based on neural network, we don't have any proof of convergence. Right? So it'd be interesting to see whether they really converge to anything interesting. Thank you.
All right, we're a bit over time, but while Lalitha sets up, any people can shout out a question or two.
Yeah.
Did I get you correct? I'm trying to now sum up what you said, that contextual data actually improve the quality of your inferences, where quality basically means the significance goes up.
The power goes up, yeah.
Can I take you out of your comfort zone by asking how that actually would relate to contextual integrity?
Can you remind me what a contextual integrity is? Sorry.
Very good, okay. Then I'll rephrase the question completely differently, because I heard you say somewhere in the beginning that when statistical power goes up, utility goes up.
Yes, so the utility is defined in terms of statistical power, right? So that's...
Sure, so I object to that, because I think whether there is utility is a question you can't answer with computation and also not assume. So you can, if you're doing research, you can say, okay, that's going to be my assumption, of course, no problem. But as soon as that research goes out into the world, I would say that the question whether the significance going up is a utility depends on...
No, I think the goal of science in general is to make discoveries, right? You want to find whether the drug is...
Discoveries are good for anything or have a utility. That's a very dangerous assumption, and in this conference, I think that is very important not to fall into that trap. So
I guess
I totally understand it in terms of a mathematical model and computational models that you want to make. You say, I'm going to assume this, but as soon as you take this contraption out into the real world, you will have to engage with people who actually live in that world to ask that question.
This sounds
I
like
think
a really
Agnes
good
is
lunch
looking at me.
discussion.
I think it's time for me to leave the stage. I'll talk to you later.
Yeah, I look forward to hearing that. All right, so we're really lucky to have Lalitha Sarkar speaking here.